Hello my dear students, today we are going to learn about some of the compounds of boron. These are boric acid, diborane, borazine and boron nitride. Firstly, boric acid. It is also called orthoboric acid. It is a weak monobasic Lewis acid of boron. It has the molecular formula H3BO3. Then what are the properties of orthoboric acid? It is a white crystalline solid with soapy touch. It is sparingly soluble in water but highly soluble in hot water. The preparation methods for the boric acid are: it can be prepared by acidifying an aqueous solution of borax. Lab synthesis of boric acid involves the addition of aqueous solution of sulfuric acid to boiling solution of borax. The large scale synthesis of boric acid is by passing the current of sulfur dioxide gas on the aqueous solution of columenite. It is also formed as a byproduct of hydrolysis of boron trihalides and diborane. Boric acid in water accepts the hydroxyl ion acting as Lewis acid, and water releases H plus ions. Thus boric acid is a monobasic weak acid. It's not a protonic acid. Orthoboric acid reacts with the sodium hydroxide to produce sodium metaborate and water. This reaction takes place at a temperature of 350 to 400 degrees Celsius. Boric acid reacts with the sodium hydroxide to produce sodium tetraborate and water. That is, boric acid reacts with the strong alkalis to form salts like metaborate and tetraborate. Next is the action of heat on boric acid. On heating above 100 degrees Celsius, orthoboric acid forms metaboric acid, which on further heating to 140 degrees Celsius, it yields tetraboric acid. At a higher temperature or red heat, it gives a glassy mass of boric oxide, also called boron trioxide or boric anhydride. The next is the reaction with the ethyl alcohol. When boric acid is heated with ethanol in the presence of concentrated sulfuric acid, the ester triethyl borate is formed. This is a volatile ester and it is vapors burned with a green-edged flame. This reaction is used as an identification test for borates in inorganic qualitative analysis. Next is the reaction with the calcium fluoride and concentrated sulfuric acid. When boric acid is heated with the calcium fluoride and concentrated sulfuric acid, boron trifluoride is formed. These are the various reactions of boric acid. Next is the structure of boric acid. The BO3 3- ion may be regarded as the basic unit of the structure of boric acid. Here the boron undergoes sp2 hybridization, so the resulting geometry is trigonal planar and the bond angle is 120 degree. Here the ground state electronic configuration of boron atom is 1s2 2s1 2px1. The excited state electronic configuration of boron atom is 1s2 2s1 2px1 2py1. Here one of the 2s electron gets promoted to 2p. Now the 2s orbital and two 2p orbitals undergo hybridization and to form sp2 hybridized orbitals. The three sp2 hybrid orbitals are used to bond with three oxygen atoms. Each oxygen atom in turn is bonded to a hydrogen atom in boric acid. Boric acid planar BO3 3- units are joined by hydrogen bonds to give a layered structure. The adjacent layers in the crystal of boric acid are held together by weak forces of attraction. Because of the weak forces of attraction, one layer can slide over the other. This makes boric acid soft and soapy to touch. Then what are the uses of boric acid? It is used as a cleaning agent, eliminates cockroaches, control termites, fire ants, fleas, carom board use, raw rice preservative, remove stains from cloth, remove odor from cloth, prevent boron deficiency in plant, and used in hydroponic nutrients. It is also used as an antiseptic in eye or ear lotions. It is also used as a nutritional supplement and as a flame retardant in the manufacture of furniture, mattresses and insulation, also in the manufacture of heat resistant glasses, glass wool, fiberglass, microwavable dishes, etc. This is all about boric acid. Here we learned about the preparation methods, properties, structure and uses of boric acid. The next topic is Diborane. Diborane is the simplest boron hydrate. Boron hydrates form one of the most structurally diverse series of compounds. Diborane has similar formula to ethane but structurally very different because it is electron deficient. In the case of ethane, carbon has 4 valence electron and 4 electrons from hydrogen. So, ethane molecule has enough electrons for 7 2-center 2-electron bonds. But in the case of diborane, it has only 12 electrons, 6 from boron and 6 from hydrogen. This makes an ethane-like structure impossible. So, here there are 2 3-center 2-electron bonds. Diborane is prepared by reacting boron trichloride with lithium aluminum hydride. Similarly, diborane is prepared by the reduction of boron trichloride with the sodium borohydride. Diborane is prepared by passing a mixture of hydrogen and boron trichloride or tribromide vapor through the silent electric discharge at low pressure or in the presence of copper aluminum catalyst at 450 degrees Celsius. In the laboratory synthesis, diborane is prepared by the oxidation of sodium borohydride with iodine. The industrial synthesis for diborane is by the reaction of boron trifluoride with sodium hydride. Diborane is a colorless, toxic, inflammable gas with a distinctive repulsive odor. Diborane catches fire spontaneously when it is exposed to atmospheric air. It burns with oxygen. The reaction is exothermic, releasing a large amount of energy. It is readily hydrolyzed by water and to form boric acid. Diborane is stable at ordinary temperature, but when heated above 100 degrees Celsius, it changes to a number of higher boranes. The next is the reaction with ammonia. Diborane reacts with ammonia and to form different products depending upon the proportion of reactants and the temperature of the experiment. Firstly, a 1:2 molar mixture of diborane and ammonia at low temperature yield diammoniate of diborane. This upon further heating yield Borazine. It is called inorganic benzene. With excess of ammonia at higher temperature, diborane yield boron nitride. With Lewis bases, diborane first undergoes cleavage and to form borane, which then react to form adducts. Next is the reaction with the carbon monoxide. Diborane reacts with the carbon monoxide at 100 degrees Celsius and under pressure about 20 atmosphere to yield borane carbonyl. Another reaction is the reaction with the alkali. Diborane reacts with the concentrated aqueous alkali and to yield the corresponding metaborate and hydrogen. The next reaction is an important reaction called hydroboration. Diborane adds to alkenes and alkanes at room temperature in either solution and to yield alkyl boranes and alkenyl boranes. This reaction is called hydroboration. The organoboranes formed in such reactions are not usually isolated, but they are converted into suitable organic compounds by suitable means. For example, alkyl boranes can be converted into alcohols by reaction with the alkaline hydrogen peroxide. For example, propane reacts with diborane and to yield propyl borane, which upon reaction with the alkaline hydrogen peroxide, it gives propanol. The next is the reaction with the ionic hydride. Diborane reacts with the methyl hydride in diethyl ether solution to yield metal borohydrides. For example, lithium hydride react with the diborane and to yield lithium borohydride. Similarly, sodium hydride react with the diborane and to give sodium borohydride. Both lithium borohydride and sodium borohydride are used as reducing agents in organic synthesis. They are useful starting material for preparing other metal borohydrides. The next one is the reaction with the halogen. Diborane reacts with the halogen and to give halodiborane and halogen acid. Similarly, reaction with the halogen acids give halodiborane and hydrogen. These are the various important reactions of diborane. Next we can discuss the structure of diborane. Diborane has a bridged structure in which each boron atom is bonded to two hydrogen atoms by regular electron pair bonds. These hydrogen atoms are called terminal hydrogen atoms. These are two center, two electron bonds. The resulting BH2 fragments are in the same plane and are bridged by two hydrogen atoms. These are called bridging hydrogen atoms. The bridging hydrogen atoms are positioned such that one lies above the plane containing the BH2 fragments and the other lies below the plane. The terminal BH bond length is 119 picometer, whereas the bridging BH bond length is 134 picometer. The terminal HBH bond angle is 120 degree, whereas the bridging HBH bond angle is 97 degree. In diborane, boron atom undergo sp3 hybridization. We know the ground state electronic configuration of boron atom is 1s2, 2s2, 2px1. In the excited state electronic configuration of boron, one of the 2s electron gets promoted to 2p, that is 1s2, 2s1, 2px1, 2py1. Now these 2s and 2p orbitals undergo hybridization. As a result, we get 4 sp3 hybrid orbitals. 3 of the 4 sp3 hybridized orbitals contain single electron and the fourth orbital is empty. 2 of the half-filled hybridized orbitals of each boron overlaps with 2 hydrogens to form 4 terminal 2 center 2 electron bond, leaving one empty and 1 half-filled hybridized orbitals on each boron. The 3 center 2 electron BHB bond formation involves overlapping the half-filled hybridized orbital of one boron, the empty hybridized orbital of the other boron, and half-filled 1s orbital of hydrogen. This is the structure of diborane. The bridging BHB bonds are called banana bonds. Diborane is used as a catalyst in polymerization reactions. It is used for welding torches. It is used for preparing rocket fuels. It is used as a reducing agent in organic reactions. It is used in the hydroboration reaction, which is a useful method for preparing hydrocarbon, alcohol, ketone and acids. Next we can discuss about another boron compound, borazine. Borazine, also known as borazole, is a polar inorganic compound with the chemical formula B3H6N3. In this cyclic compound, there are 3 BH units and 3 NH units alternate. The compound is isoelectronic and isostructural with benzene. For this reason, borazine is referred to as inorganic benzene. Like benzene, borazine is a colorless liquid. There is a close similarity in the structure of borazine and benzene. We can compare both benzene and borazine. Benzene is an organic compound, borazine is an inorganic compound. The benzene molecular formula is C6H6. The borazine molecular formula is B3N3H6. Both are colorless liquid. Benzene and borazine are isoelectronic with each other. Benzene is less reactive, whereas borazine is more reactive. Benzene is thermally stable, whereas borazine is thermally less stable. Benzene undergoes substitution reactions, whereas borazine undergoes addition reactions. Benzene ring contains only carbon atom, whereas borazine ring contains alternate boron and nitrogen atoms. Benzene is a non-polar compound, borazine is a polar compound. Benzene does not undergo hydrolysis with water, but borazine undergo hydrolysis with water. Next we can discuss about various methods for the preparation of borazine. Borazine can be prepared by heating a 1:2 molar mixture of diborane at 250 to 300 degrees Celsius. The another method is borazine can be conveniently prepared by heating lithium borohydride with ammonium chloride at 230 degrees Celsius in vacuum. Now we can discuss the properties of borazine. We have already told that borazine is not thermally very stable. It decomposes slowly on storage even at room temperature and to yield diborane, hydrogen and other volatile products. The next one is the reaction with bromine. Borazine, when heated with excess of bromine at low temperature, adds 3 bromine molecule and to yield B-tribromo, N-tribromo borazine. When the above bromine adduct is heated to 60 degrees Celsius, it decomposes and to give B-tribromoborazine. Borazine is far more reactive than benzene. With hydrogen chloride, it forms an adduct, whereas benzene is unreactive towards hydrogen chloride. Benzene does not undergo this type of addition reactions. At high temperature, Borazine undergoes hydrolysis and yield boric acid, ammonia and hydrogen. Next, we can discuss the structure of Borazine. Borazine has a hexagonal planar structure very similar to that of benzene. In Borazine, the boron and nitrogen atoms are alternatively placed in a planar hexagonal ring, in which the bond angle is 117.1 degree at the boron atoms and 122.9 degree at the nitrogen atoms. This is very close to the CCC bond angle in benzene. The BH bond length is 120 picometer. The BN bond length is 144 picometer, which is very close to the CC bond length in benzene, which is 142 picometer. From the bond angle, it is clear that the Borazine does not form a perfect hexagon. This is because of the electronegativity difference between boron and nitrogen atom. The electronegativity of boron is 2.04. The electronegativity of nitrogen is 3.04. There is an electrode deficiency on the boron atom, and the lone pair on nitrogen favor alternative mesomer structure for Borazine. These are the mesomer structures for Borazine. The structure of Borazine is similar to that of benzene. In Borazine, each boron atom and nitrogen atoms are sp2 hybridized like carbon atoms in benzene. But the difference is that the pi bonding in Borazine is dative and arises from the sidewise overlapping of fully filled p orbitals of nitrogen and empty p orbitals of boron. But in the case of benzene, the pi bond is formed by the overlapping of singly occupied p orbital of carbon atoms. We know nitrogen is more electronegative than boron, so each nitrogen receives more sigma electron density from the neighboring boron than it gives away as a pi donor. The net effect is that the charge density on the nitrogen increases. In addition, nitrogen retains its basicity and boron its acidity. Borazine is more susceptible to nucleophilic attack at the more positive boron and electrophilic attack at the more negative nitrogen atom. These properties make Borazine more reactive than benzene, and it undergoes addition reactions while benzene does not. In both the benzene and Borazine, the pi electrons are delocalized over all of the ring atoms. Because of the electronegativity difference between boron and nitrogen, more electron density is located on the nitrogen atom. Due to this partial localization, the pi bonding is weakened in the ring and undergo addition reaction. Next boron compound is boron nitride. It is commonly used as a refractory material. It consisting of boron and nitrogen covalent bonds. Boron nitride is a chemical compound that is isoelectronic and isostructural to carbon with equal composition of boron and nitrogen atom. Boron nitride was generally compared with other carbon allotropes. There are two types of boron nitride, cubic form and hexagonal form. The cubic form of boron nitride has a diamond-like crystalline arrangement, and the bulky crystal of hexagonal boron nitride is analogous to graphite crystal. Mainly, there are three methods for the preparation of hexagonal boron nitride. Firstly, boron nitride can be prepared by heating diborane with the excess of ammonia at high temperature. The second method is the boron nitride can be prepared by heating boric oxide with ammonia at 1000 degrees Celsius. And the third method is boron nitride can be prepared by passing nitrogen through a mixture of boric oxide and carbon heated in an electric furnace. Cubic boron nitride is formed by high pressure, high temperature treatment of hexagonal boron nitride. Here the pressure used being between 5 to 18 gigapascal and the temperature between 1730 and 3230 degrees Celsius. Then what are the properties of boron nitride? These are white crystalline solid. This is very stable and unreactive substance. It has excellent thermal and chemical stability. Next we can discuss about hexagonal boron nitride properties and their uses. The hexagonal boron nitride has excellent lubricating properties. It does not conduct electricity because of the absence of perfectly delocalized conducting electrons in it due to the significant electronegativity difference between boron and nitrogen atom. Hexagonal boron nitride is thermodynamically more stable than cubic boron nitride. But the conversion rate between hexagonal boron nitride and cubic boron nitride is extremely negligible under ordinary condition. Hexagonal boron nitride is used in high temperature resistance lubricants, high temperature resistance paint, special resistors for high temperature conditions. It is also used as a starting material for the preparation of cubic boron nitride. Then what are the properties of cubic boron nitride? It is the second hardest material known, inferior in hardness only to diamond. It has excellent thermal conductivity and chemical inertness. It is used in machine cutting tools and abrasives. It is also used in making crucible, reaction vessel as well as in wear resistant coatings. The powdered boron nitride properties are soft, sheen and non-toxic. Due to the softness and sheen of powdered boron nitride, it is used in the cosmetics and personal care industries. It is also used in polishes and lipsticks. It is also used in creams for hiding wrinkles because it is light reflective properties scatter the light, making the wrinkles less visible. This is the hexagonal boron nitride structure. The hexagonal boron nitride structure is a layered lattice structure which is similar to that of graphite. In the hexagonal boron nitride structure, there is a hexagonal arrangement of boron and nitrogen atoms in each layer. The boron and nitrogen atoms are bound by strong covalent bonds. The layers get superimposed on one another such that the boron and nitrogen atoms are alternatively above one another. In the hexagonal boron nitride structure, the layers are held together by weak van der Waals forces. The boron-nitrogen bond length is 146 picometer and the distance between the layers is 333 picometer. The crystal lattice structure of cubic boron nitride is similar to that of diamond. Here, each boron is tetrahedrally surrounded by 4 nitrogen atoms and each nitrogen atom is tetrahedrally surrounded by boron atoms. The boron-nitrogen bond length is 155 picometer, which is very close to the Cc bond length in diamond. This is the structure of hexagonal and cubic boron nitride. Today we have learned about some compounds of boron such as Diborane, Borazine, boric acid and boron nitride. I think it will be helpful for you. Thank you.